Oh, guys, nice to see you. Good afternoon.
Good afternoon.
Hi. Good afternoon. Let's wait maybe 1 minute so more people can join. Okay, hello everyone. Nice to see you again on our discussion. And just short reminder of our previous lecture. So we introduced, like we started new topic, gravitation, introduced the equation which quantifies gravitational force in terms of masses of two bodies which interact with each other with gravitational interaction. And so it's proportional for two particles with masses m1 and m2. Gravitational force is proportional to the product of these masses and reversely proportional to the square of the distance between these two particles. So there is a proportionality coefficient, capital G, which is a gravitational constant. And also we introduced and discussed in details with explanation why these statements are true. We introduced three Kepler's laws, which are based on empirical observations. And after analysis of these long-term observations, Kepler came up with this dependencies for different parameters which are involved there and describe motion of planets and satellites about sun or about their planets respectively. So today I would like to come back a bit to this equation which describes gravitational force and give you a bit of like step-by-step explanation how you can, based on known Kepler's laws and laws of motion, how you can come to the derivation of this gravitational force equation, and we will see how actually this was done by Newton in his original work. So let us maybe switch the screen and let's discuss this. So first of all, before we start this kind of explanation of this equation, we need to highlight first thing that first Kepler's law claims that all planets move rotate about the sun following some elliptic orbits. That is true. However, it is necessary to underline that most orbits, like orbits of most of the planets in solar system, they are elliptic, all of them, but most of them are very close to circular orbits. So this eccentricity of these elliptic orbit is quite small, so it's not far from zero. It's obviously not zero, but most of planets possess almost circular trajectories. And that's why it's really makes sense to consider as a simplified model just a circular trajectory. And in this case, if we stick to a circular trajectory, like circular orbit, according to the second Kepler's law, we remember that it states that the position vector sweeps equal areas per equal interval of time. And if we apply this to specifically circular orbit, that means that planets move about the sun with constant linear velocity. So means that if there is no any angular acceleration or tangential acceleration, then for each equal interval of time, the radius of the circle will sweep equal area, and that will require constant linear velocity. So now we come to the third law of motion, and third Kepler's law. And third Kepler's law tells us that there is proportionality between square of the period of rotation and radius of this circular trajectory in third power. So means, in other words, that we can write the following. The ratio of t squared over r cubed is some constant. So now let us recall the equation which describes centripetal acceleration in terms of linear velocity and radius. We can write that centripetal acceleration is equal to v squared divided by r. From other point of view, we can also express linear velocity as 2 pi times r divided by t. So it's length of the circular trajectory in the numerator, and time it takes to make one circle about the sun, if we consider some planet moving about the sun, which is this period t. So we can write that centripetal acceleration in second power will be equal to 4 pi squared times radius of the orbit divided by t squared. So now we have expression for centripetal, sorry, it's not square, it's a just for centripetal acceleration. So we substitute this expression here in v squared. So we get expression for the centripetal acceleration. And now once we have it, we can recall the second law of motion. So we know that any acceleration is equal to some force divided by mass. So in this case, we have centripetal acceleration, so we need to deal with some centrifugal force. And we can write that, let's call it like with this, let's mark it as centripetal acceleration. then it will be centrifugal force divided by mass. So we consider just absolute values of these forces and acceleration. And that will be equal to this expression in terms of radius and period of rotation about the sun. So we can write that it's equal to 4 pi times r divided by t squared. Okay, according to the condition.
Shouldn't it be p square?
Yeah, p squared, sorry. Thank you. 4 pi square times r divided by t squared. So now we consider that this system, the sun and the planet, and the planet's circular trajectory is in equilibrium condition, in some steady state, so it doesn't change. In that case, we can write that in terms of absolute values, this centrifugal force should be compensated by gravity force, because otherwise this planet would just either fly away or fall eventually on the sun. So there should be this balance between forces. So we can, when we deal with absolute values, we can substitute Fs with Fg with gravitational force, because in the magnitude they are equal under steady state condition. So now let us write it here. We can write gravitational force divided by mass is equal to 4 pi squared times r divided by t squared. And next, what kind of convenient to do in order to have the right combination of parameters in the left and right side. Let us multiply left and right side by r squared. So we will get the following. Will be F gravitational force times r squared divided by m, and will be 4 pi squared times r cubed divided by t squared. So as you see, this ratio is actually from the third Kepler's law. This ratio is constant, t squared divided by r cubed, or in the contrary, r cubed divided by t squared. Doesn't matter, it is a constant. 4 pi square also a constant. So it means that the right side of this equation is some constant. And taking this into account, we can express now the gravitational force. So we can write Fg is equal to some constant times some mass, which we haven't yet defined which mass, divided by r squared. So with this mass, so we didn't define it initially, we just operated with the equation which is the second, defines the second law of motion. However, it is obvious that since we have gravitational interaction, both masses of the planet and of the sun should be involved. So quite obviously that in this under this mass should be the product of these two masses of the sun and the earth. So we can write that we have some constant mass of the sun times mass of the planet, let's call it like this, and it will be r squared. And you see that if we compare this with the equation for the gravitational force, r squared, this constant is actually the gravitational constant. So initially, this constant was not known, obviously. So you get some expression for gravitational force in terms of mass of two objects and distance between them. But the constant was unknown. Later, British scientist Henry Cavendish, it was like 1798, he determined experimentally this in his famous experiment with like suspended two masses and calculating the torque of which is caused by gravitational interaction. He calculated the value of this constant with quite decent accuracy. So, but initially you see that the equation for gravitational force with, of course, some constant unknown could be derived based on three Kepler's laws, which were obtained empirically without any theoretical models initially behind them. So it's just pure observation. And also empirical, also based on experimental observations, laws of motion. So this is the idea how both of this set of laws can be combined in order to approach the derivation of gravitational equation for the calculation of the gravitational force. Okay, so now we can proceed further and consider such concept as gravitational field. So main question in terms of this gravitational force is how is it possible that two bodies which are not in contact with each other can interact with each other with this gravitational force via gravitational force. And that's really counterintuitive because we have some friction force when we have contact with two bodies. We have some like deformation of bodies when they hit each other, and that creates some spring force which pushes them backwards. So all these type of mechanical forces, they require direct contact between bodies in order to have any types of interaction, in order to exert any forces on each other. However, with gravitational force, it's completely different because objects can be located at any distances from each other without interaction, but still like without contact, but still they interact with each other. And this interaction can be quite strong, depends on the mass and distance between these bodies. So the like Newton originally, who derived this equation for gravitational force, didn't have answer to this question, and that came actually later, how exactly this interaction is possible, and that was explained with the concept of gravitational field, where we have some parameter which is strength of gravitational field, so something similar to other concepts like electrical or magnetic fields, but that was to come many decades later. So that's why it was not so straightforward to explain the reason why object can interact without being in contact. So in the scope of this concept of gravitational field, there is some quantitative parameter which describes this gravitational field, and this is strength of gravitational field, which is a vector parameter, and we can think about this in the following way. So if we place some object with mass m inside gravitational field, there will be some force acting on this, like with gravitational force, obviously, acting on this body with mass m. So the strength of the gravitational field, which is g, we call it acceleration of free fall on the Earth's surface, but in other words, to be more general, that is strength of gravitational field on the Earth's surface. That will be equal to gravitational force divided by mass of the object. So taking into account the expression for gravitational force, then we can write also expression for the strength of gravitational field. That will be minus gravitational constant g times mass of the Earth. So this is when we consider strength of gravitational field on the surface of Earth, divided by X surface, or we can maybe consider any distance from the Earth. So we consider Earth, and then at any distance r square, and here is we need to multiply this by r vector, which gives us the orientation of radius vector, like position vector, and this minus tells us that this gravitational field is pointed towards the center of the planet. So if we have some gravitational field, we definitely have some potential energy associated with this field. And let us calculate it in general case, because if we consider some limited case of application, we can write, so far we were doing this, we were writing that potential energy on some object above surface of Earth is equal to mgh, which is h is the height from the ground level, Earth's surface, to this position where the object is located. However, in general case, objects can be far away from the surface of the planet, and this g is a function of this distance, this position, radius r. So in order to take this into account, we need to discuss some general case of potential energy of gravitational field. So change of potential energy by definition, like difference between final and initial potential energies, is equal to negative work done by internal conservative force in the system. So we have system of the sun and the Earth, or we have system Earth and some object next to this the planet. So there is some internal conservative force, which is gravitational force, and this is a function of distance times dr. So from r initial to r final. So let's say we have some planet with radius r and mass me. So let's first planet Earth, and we have some object next to the planet with mass m in point A. So when it moves to some new point, let's say point B, here we have some gravitational force acting on this object from the side of the planet. Obviously, here will be also some gravitational force. And while this object is moving from initial to final position, there will be some work done by this conservative gravitational force, which is in this case considered as internal force of the system. So we can write for gravitational force for this, which we have in the integral as a function of r minus g times mass of the planet times mass of the object divided by r squared. So this minus here stands for the fact that this force is attractive. So this gravitational force attracts object towards the center of the Earth. So we can then write for the difference of final and initial potential energies as g times mass of the planet times mass of the object. These are constants, we take them out from the integral. Then we have here integral of like from in the range from initial and final position vectors. And here we will have dr over r squared. So if we integrate this, we will get the following. So our constants first, then we have minus 1 over r from r initial to r final. So this will be equal we can now put this minus in front, will be minus g times m mass of the planet times mass of the object. And here we will have 1 over r final minus 1 over r initial. So it is in any kind of field, including this gravitational field, any potential field, we can define arbitrarily where is the zero potential. So in this case, we can consider that Ri initial position of the object when it's located somewhere very far from the planet approaches infinity, then initial potential energy approaches zero. So at the infinitely large distance from the planet, the potential energy of the gravitational field is approaching to zero, which makes sense because of the fact of this huge distance, the potential energy approaches to zero. So in this case, if we consider Ri, which is in denominator here, approaching to infinity, and initial energy approaches to zero, we can write the final expression for the potential energy of gravitational field. Like that will be just potential energy as a function of position, and will be equal to minus gravitational constant times mass of the planet times mass of the object divided by r. So we have potential energy is negative because the force is attractive. So there should be done some work or to overcome this potential energy to leave the planet. And so this we wrote for the planet object system, but that is also valid for any combination of two objects. So in general, we can write that this will be equal to, maybe not this, let's write separately, potential energy of gravitational field will be equal to minus g times m1 times m2 divided by r. So it's proportional to the product of two masses and reversely proportional to the distance between these objects. If, for instance, we have some system of more than two bodies, let's say we have a system of three bodies, we have body 1, body 2, and body 3, and there are different distances between them, so it will be r1, 2, r1, 3, and r2, 3. So then potential energy, which is kind of accumulated because of gravitational interaction of these three objects, would be three planets, for instance, in order to take them apart from each other to distances which are these distances approaches to infinity. That will define this work to be done to take them apart from each other, will define the total potential, gravitational potential energy. And that is just sum of potential energies of interaction between each of these objects. So it will be potential energy of interaction between 1, 2, 1, 3, and also 2, 3. So that will be minus g times m1, m2 divided by r1, 2 plus m1 times m3 divided by r1, 3 plus m2, m3 divided by r2, 3. Okay, so this was about potential energy of gravitational field. And now let us consider this, make some energy consideration in planetary and satellite motion. So let us go to a new slide and consider some big mass, like some massive object, and some small object with mass m, which is moving about this massive object with some, here is linear velocity, and here is the radius position vector. Let's assume that this massive object is much heavier than the small object. So because then we can assume that this massive object neglect with the rotation about the center of mass. So it will be with respect to some inertial system of reference, we can assume that this velocity of this massive object is zero. Then there is only motion of the small object about this massive object in the center. So in that case, we want to define what will be the total energy of the system. And that will combine kinetic and potential energy. So for kinetic energy, we know expression. It's m mass of this object, which is moving, times v squared divided by 2. And for potential energy, we just derive this equation on previous slide. That will be minus g times m times masses of the two objects divided by r. So this is the expression of total energy of the system. And let us now consider that under stationary conditions, equilibrium, steady state conditions, gravitational force should be equal to centrifugal force, MA. Here we can write for gravitational force G times M times M divided by R squared. And for the centrifugal force, we can write mv squared divided by R. So now, in order to make this convenient for us form, let us multiply this by R divided by 2. So in this case, what do we get? We get, if we consider the right side of the equation, we get mv squared divided by 2, which is equation for kinetic energy. That will be equal to G times M times M divided by 2R. So we have R squared here in denominator and R here in numerator. So if we get this expression, now what we can do, we can simplify equation for total potential energy by substituting kinetic energy with equation in terms of gravitational constant, mass, and radius. So if we do this, we will get the following. So it will be G times M times M divided by 2R. So this is instead of mv squared divided by 2 minus G M times M divided by R. And that will be minus G times M divided by 2R. So we see from this equation that total mechanical energy of the system which interacts with gravitational force is equal to minus G m divided by 2r. So it's defined actually only by the masses of objects which are involved in this system and radius, like distance between the objects. And because of this system is isolated, there is a conservation of energy and angular momentum. This value is constant. So that means that potential energy, the total energy of the system before and after some changes, for instance, in the radius of orbit or mass of the object, which is following this circular object, the total energy should remain constant. And that's why we can write here, for instance, 1/2 mv initial square minus g r initial. So let's say we had initial velocity and initial radius. Then we change velocity and radius. So they can change not just randomly, but they should change in that way that the total energy is conserved. So it will be equal to 1/2 mv final square minus g divided by r final. So this fact of conservation total energy of the system of two bodies interacting via gravitational field could be used in order to solve some practical problems involving changing of one parameter and asking what will be the change of how other parameters will change. So assuming that this energy is constant, this could be a nice approach to solve such problems. Okay, now let us consider maybe one more important question, which is escape speed for, let's say, some projectile with initial velocity at the surface of the planet. What speed it should possess in order to leave the surface of the planet, considering this conservation of mechanical energy concept which we discussed right now. So let's say we have planet with some radius. Let's use it, maybe capital radius. Let's consider Earth. Radius of the Earth. There is some object on the surface. This projectile gained some initial velocity upwards. Then we are interested, for instance, when the object of this projectile will be equal to 0, and which height it can move upwards. Assuming that there is no friction in air and neglecting with the motion of the Earth itself, because that will also make a difference. So we have some steady condition when just this projectile which is moving upwards and gravitational field of the Earth which keeps this projectile with mass m. And here we have mass of the Earth. So initially, what do we have in our total energy? So we have contribution from both kinetic and potential. So we can write 1/1/2 times m v initial square, like mass of the projectile, minus g mass of the Earth times mass of the projectile divided by radius of the Earth. At final stage, we will not have any kinetic energy because we are interested in the moment when kinetic velocity is equal to 0. So then we can write that there will be only potential energy, which is g times mass of the Earth times mass of the projectile divided by radius maximum. So it's maximum distance from the center of the Earth, and that could be defined also as minus g times mass of the Earth times mass of the projectile divided by radius of the Earth times this h, like height from the surface of the Earth to the point where the projectile will reach the velocity equal to 0. So I guess since we are running out of time, we don't want to be in a hurry with this. We will start from this point our discussion on Friday, and we'll discuss this in more details, the derivation of the escape velocity. If you have any questions, you're welcome. So we first of all discussed in details the way how you can approach the derivation of gravitational equation for gravitational force based on the empirically obtained and formulated equations which are coming out from laws of motion and Kepler's laws. Yeah, sure, there's a question. This will be also recorded and available online, this lecture. And we want to keep this opportunity for students to have this asynchronous learning experience. So that's why all lectures will be available online for everyone, if you're interested. And also we introduced the concept of the potential energy of gravitational field, which is the reason why the gravitational field is the reason which explains the physics behind interacting of two objects without being in contact with each other. So which happens with this gravitational field and gravitational force. So since there is some attracting gravitational force in this, when we place object with some mass in gravitational field, there is associated potential energy, which we discussed and calculated, and considered that the total energy, kinetic plus potential energy of isolated system of planet and satellite or sun and a planet is equal to some constant value defined by the mass of the objects which are interacting and distance between these objects, and that this energy is conserved since the system is isolated. So based on that, we approach the derivation of the escape velocity, and we will finish this during our next discussion. Okay, thank you very much for attention. Nice to see you all, and hope to see you during our next discussion on Friday. Take care, and see you next time.
Thank you. Goodbye.
Bye-bye.
Thank you.
Goodbye.
Goodbye.
Thank you.